Hello and welcome to this webinar on language features of version 18.0. This is the fifth in the series. I'm going through all the new and improved primitives, system functions, and an IBeam as well. Here's a brief overview of all the features that this series covers. And these are the ones that I've gone through so far. You can find the previous webinars on dialog.tv. So today I'm going through extensions to Partitioned Enclose and mix with access. Before we continue, I'm turning unboxing, so to say. This is because we're going to deal with nested arrays, and it makes it much easier to see what exactly is going on. Partitioned Enclose. So really what we have added in a nutshell is the ability for Partitioned Enclose to produce empty sections in the data as it gets split up. Since day one of Partitioned Enclose, the left argument has been a Boolean vector where the ones were indicating which elements of the right argument were to become the first element in a segment. Now what we have done is, so to say, to reinterpret that left argument. So instead of indicating which elements are beginning the new sections, then we are saying for each element how many sections begin right before this element. And so for 1 and 0 it comes out the same. Now 1 means since a new section begins right before this element, then this element becomes the first element of a section. A 0 means no new sections begin right before this element, and that means this element becomes part of the already ongoing segment, if any. But this allows us to increase the number above 1 and say that 2 new segments begin, for example, for with this element's position. That means 2 new sections begin right before. Or in other words, 1 empty section is being inserted before this element, and this element is then the first element of the second section. And if you look at it with boxing on, then in essence it's just a count of how many of these vertical lines go through the array right before this element. So here's an example. Let's say that we have some categories, some cutoffs of numeric values, and then we have some actual values. And we want to split the data into runs that correspond to these bins, to these groups. So we start off by using the interval index, and that gives us an indicator number, an index into the runs, the ranges that are being defined by these cutoffs. So we can see the ones say that these 3 numbers, 3, 14, and 15, belong in interval number 1, and 35 belongs in interval number 2. There are no numbers that belong in interval number 3, and so on. And so what we're looking for here is partitioning our values such that runs of identical bin numbers belong together. However, there's a problem with the missing ones, because we also want to have an empty run of numbers belonging in that group between 40 and before 60. And so these highlighted stops in between, that's where we want to insert breaks in the data. And we want to know how many breaks to insert. And we can do that by doing a pairwise difference over the bin numbers. So that tells us how many bin numbers do we increase for this element. And so if we increase the bin number by 0 for this element, that means it belongs in the same bin as the previous element. If we increase it by 1, it means that this element is the first element of a new bin. And by 2 means we've skipped 1, and now we're starting another one. And of course, our very first element needs to go into a bin as well. It doesn't matter what, or it doesn't even make sense to say what the previous one was. So we always start 1 there. So we add a 1 in the beginning. And then we can apply partition enclose. And now with the extension, it works. And we got our data put into these runs that they belong in. And actually, this formula comes out as a nice train as well. It fits well into the pattern of trains. Traditionally, you might have gone with using the key operator for doing such a thing as this. But there are several issues with that. One is that you have to mangle the results a little bit and the data a little bit, because key doesn't know what, should we say, the full set of possible values are. So you have to insert in order one of each, which are the indices of the count of things, and then there are the edges. There could be something that falls outside of the whole range, and you have to account for that. So you actually have to apply a lot more modification, and it ends up both longer and much more involved. And as you can see here, the performance is also not good when compared to the method of using interval index with partition enclose. Another example of doing this is that we start off with indices of where we want new partitions to begin. And as you've seen in the previous webinar in my series, we can use the where primitive in reverse to change this into a mask that tells us where we want to start. Now, where doesn't know the length of the original data. If we stack it on top using mix, then mix will pad the mask with additional zeros at the end, and that gives us just the right amount of zeros that we need in order to run partition enclose. So here's an additional extension we've done to partition enclose, which is allowing it to imply trailing zeros if there are missing elements. So we don't have to pad with extra zeros. It will understand that what we want to do anyway. What if instead of one of each of the indices we have multiple? So this means when you have duplicates in the indices where we want partitioning to begin, where we want the segment to begin, it means we want to have some empty segments there. And again, with the extension to where with inverse, then it will count how many of each index are there. So this is basically, there's 1 1 and 0 2s and 0 3s and 2 4s and 2 5s. And that again works with partition enclose. So we're saying we're starting 2 segments in this position. And the last extension we've done is if you want an additional sectioning, additional partition to begin after the last element, then you can supply a number, 1 if you just want one empty segment at the end or more, corresponding to that missing element at the end. So that means that the mask for partition enclose can be 1 longer than the data along the axis you're partitioning on. And that very last element indicates how many sections, trailing sections, you want to be empty. So you can see here we added 1 empty section. That's the extension for partition enclose, and all types of partitionings where we preserve all the data can now be defined in terms of partition enclose. Okay, the very last extension is mix with an axis. I'll try to take it really slow because this gets complicated. Feel free to participate in the chat and ask questions, and Richard Park is on standby to forward your questions to me. This can get involved. If I'm going too fast, you can let me know as well. Now, because we're going to deal with high rank arrays and length 1 axis, I'm going to turn boxing on to the max level. That's not something I usually use, and it's not the default because it is very verbose, but it does give us somewhat more clarity for special arrays. And let me quickly explain how this works. With the max style of boxing, we always get these frames around arrays, and we also get indicators for the axes involved and also the types, which we don't need for this part. I've added one more embellishment here that you don't get in the session, and that is some coloring. I've shaded the axis lines with as many characters worth of shading as that axis is long. So you can see here there are this many characters, and that means we have shaded the whole thing to this. So here it's pretty trivial, but later you'll see that it becomes useful. And so the way boxing works is that if we have a vector, then we have that one axis going across the screen, and this is a length 3 one. If we have a matrix, then we get an additional arrow pointing down, which is the direction of the leading axis, and then the second axis, which are the columns, goes across. And so notice here, it's important this extra embellishment of the additional axis, because otherwise we would not be able to see the difference between the vector and the one row matrix. So increasing the rank, here is a rank 3 array. And this is of course hard to project a rank 3, that means a 3-dimensional item onto a 2-dimensional screen. Boxing is doing this by drawing an additional line on the left for a leading axis, and this can be a little bit hard to interpret. What this actually means is that we have 2 layers. So each layer is a 1x3 matrix, and we have 2 layers stacked on top of each other. So it helps if you think about that additional line that's, for technical reasons in a text-based environment, can only be straight. You think of it as being like going into the screen, like that. And finally, we have inside this for each layer we have 1 row and 2 columns, but there are actually 2 rows involved here because each layer has a single row. So this axis indicator is only an indicator of the axis on the whole array, not for each layer in the array. And then finally we have the columns as before. Stepping it up, here is a 4-dimensional array. So this is where you have to be careful about it. This can be hard to imagine in our everyday world what a 4-dimensional array looks like, but you can think of it as representing things. So if you think of a 2-dimensional array as a page of letters, where you have rows and columns of letters on the page, and a 3-dimensional array would be like a book, where you can choose page and then choose line and then choose column. Then a 4-dimensional array would be a collection of books, say a shelf of books. And again, boxing will add additional vertical lines on the left, starting with the leading axis. So the leading axis here is length 2. And that means we have 2 major cells, each of which is a rank 3 array, a block of data, so to say. So these are the 2. And the empty lines here, you can see a different size empty lines. They indicate different breaks in dimensionality. So the double line spacing between DEF and GHI, it indicates that there are 2 dimensions difference here between them. And then going in 1 level, we have a by 2, so it's a 2 by 2 by something more array, and it's a length 2 axis like before. So every one of these 2 blocks has 2 layers, and that means there are 4 layers in total because the 2 major cells, 2 layers each. And then finally, each layer is a 1×3 matrix. Okay, with that out of the way, let's start mixing shapes. Here is an involved array. It is a matrix of matrices. I'll put it over here. Let's analyze this array a little bit. The array's outer shape, you say the shape of the whole array, is 1×2. It's a 1-row, 2-column matrix. And the elements, it being uniform, are 3×1 matrices. So they are 3-row, 1-column matrices. And so what the mix primitive does is that it increases the rank of the array. It's kind of mnemonic that the arrow points upwards in that it increases the rank. And you pay for that additional rank with depth. So depth is currently 2, and we're going to get rid of that depth, and it becomes a flat array of depth 1. And the way the axes are assembled here is that the outer array forms the leading axis in the result, and the inner arrays form the trailing axis in the result. So if we take the outer shape and we stretch it out a bit, so then our outer shapes hold their positions from the beginning, and then we slot in the inner shape as trailing axis. That gives us our result. So this is how mixing works. The thing is that you can specify an axis, and this is where it gets a bit complicated. So the default axis for mixing is just after the index of the last outer axis. So because we have a rank 2 array as the outer array, then the default axis is between 2 and 3. So for example, 2.5. It doesn't matter. But we can specify something else. We can specify that we want axis, for example, 1/2, which is right before 1. So again, we start off with our outer shape, and then when we mix it like this with axis 1/2, it can be hard to understand and interpret what the result is here. But what's happening is that in order to place the inner shape into the framework of the outer shape, to mix the shapes, we take these values and look them up in the axis where they need to go, and we find out they need to go into slot 0.5 means right before 1, so then they become leading axis. We can also use 1.5, and again it looks kind of funny, but it means that when we go and look where should we insert these axes, it's between axis 1 and axis 2. So that's where we push them apart and we insert additional axes in between. And then the data, so to say, gets poured into this mold in this order of the axis. Okay, let's go back to the normal mixing with default axis. So what this has already been possible all the time. What's extended in version 18 is that we allow the APL2 convention of specifying axes for mix, even if you do not change the migration level. So even in the default migration level 1, meaning that mix is still denoted by the up arrow, you can now use the APL2 convention. The APL2 convention is very easy to know what the corresponding value in the APL2 convention is from the Dyalog traditional value, because it's simply rounding that value up. So instead of it being 2.5 or 2 point something, it's simply 3. And sorry, this doesn't quite look right. Just give me a second here. Okay, well, we are. What's going on here? So sorry about that. Technical glitch here. There we go. Okay. So let's go back. Right, with 3. So now, if we, the same thing goes for x is a half. The corresponding APL2 value is x is 1. But what this really means is not just a rounded up value. What it really means is that we are placing the new x's into specific slots. So we're saying when we're inserting our inner x's into the shape of the final result, the new x's begin at position 1 in the shape of the final result. What's the benefit of this? Being that it's just a matter of changing the values slightly. Well, this allows us to specify, when we have multiple x's, to specify them separately. So now we are saying that the first of the inner x's goes into slot 1. The second of the inner x's goes into slot 2. And then since the outer rank was 2 and the inner rank was 2, means that the result must have rank 4, then the only remaining slots for additional shape are trailing ones, and that means that the original outer shape falls into those 2 remaining slots, and our result then has the inner axis as leading axis and the outer axis as trailing axis. Now, why would you want to do this? Because this allows you to break away from inserting the new inner axis in consecutive and increasing order. So, for example, we could spread them out and put them in reverse. So now when we are trying to insert the inner axis into the final result, we are going to look at the first one, and it goes into slot number 4. And then the second one goes into slot number 2. And then there are 2 remaining slots, and those 2 slots are then used in order for our original shape. But this is flexible. But I actually think there is a better way to do this. If instead we use the normal mix, which is, I think at least, easier to comprehend, that we are simply tagging on the inner shape to become trailing shape, then we can use the Dyadic transpose to reorder the axis. In fact, some people prefer calling Dyadic transpose reorder axis. And now, when we assemble the result, then remember that the outer axes are the leading ones to begin with, and the inner ones are the trailing ones. And Dyadic transpose tells us which position should these axes go into instead of their original position. So we start off with the first axis from the outer shape, and that goes into slot number 3. And the second shape from second axis from the outer shape goes into slot number 1. And then we proceed to the first axis of the inner shape, that goes into slot number 4. And the second into slot number 2. And this means that using Dyadic transpose allows us to, in one operation, both place the inner x's where we want them to go, and place the outer x's where we want those to go. If we go back for a moment, you'll also notice that after we place this, you can see a correspondence between what's inside the bracket axis for mix and the trailing axis for transpose. And this is simply because mix with axis is telling APL where we want the new axis, the inner axis, to go into the result. And Dyadic transpose is being explicit about everything. It's saying where we want all the x's to go into the result. And that's why the two last elements in our case correspond exactly to those two elements that are inside the brackets in mix. So again, using Dyadic transpose allows us to place each axis into the exact position we want it to go. And then we can just mix like normal. So I think this demonstrates really the power of Dyadic transpose. It is one of those tools that is a foundation stone in mastering array programming. And so, while this webinar is the last in my series of new features in 18.0, there will be an upcoming webinar, it's not the next one, that will in a way pick up where this one leaves you and put together Dyadic transpose with the rank operator, which is the other fundamental building block of array programming. And once you master putting these two together, then you will have full control, being able to manipulate arrays in any way you can imagine. So, that's what I wanted to go through today. I know it's complicated stuff, but of course you can always go back and look at it again. Please ask any questions you might have in chat about these two. So, this concludes my going through all the new and improved language features of Dyalog APL version 18.0. The next webinar is going to be Richard Park continuing his series on thinking in APL. And of course you can use these tools that you learned over this to then apply your thoughts on the arrays. APL is very much geared for letting you express your ideas. It gives you a notation to express your thoughts. If there will be no questions, then the only thing that remains is for me to so Tony is saying mixing like normal, right? So again, mixing like normal, it simply means opening up the enclosures that we have in or the outermost enclosures that we have in an array, and letting whatever axis that we have there, if any, become part of the outer shape. And yes, it is slightly complicated, but I think it is at least much simpler to deal with than mixing with axis, where where the shapes from the inner and the outer arrays are getting mixed up. And then once you've got a flat array to work on, at least an outwardly flat array, then you can use Dyadic Transpose. And mastering Dyadic Transpose, it's not easy, but it is definitely possible to do, and it gives you a lot of freedom. So, thank you so much for watching.